Hello and welcome to this lecture on KDB plus Q by myself, Paul Billiken. I'm your instructor. I have been a quant for more than 2 decades, and and I have been a KDB expert for pretty much all of this time. So we're going to think in this lecture what KDB plus Q is, and we're going to introduce the terminology. So by the end of this lecture, you will really know what you're talking about. When you talk about the nomenclature and history of Q, you will know what KDB is, what Q is, how the two are different, how the two are related, and that's precisely what we will talk about today. We'll also understand where KDB is in the overall ecosystem of programming languages, which niche it occupies. That's the kind of stuff that we will cover in this lecture today. So it will be, there will be quite a bit of history, but I think that's the kind of background that you do need to know so that you can converse knowingly and confidently with other KDB experts. First of all, on this slide, you see a photo of Arthur Whitney, a computer scientist, a Canadian computer scientist that was born in 1957, and he is the author of KDB Q. Okay, so what is it? What is KDB? KDB Plus is a database built on top of an interpreter for a programming language Q. Both were created by Arthur Whitney, and they have been developed and maintained since 1993 by the company KX Systems Incorporated, which used to be a subsidiary of First Derivatives plc. Why was it created? With the aim of addressing the inability of traditional relational databases to keep up with increasing volumes of data and speed requirements. Now, here is a quote from a KDB expert, Nick Saris. A typical database installation requires 3 teams: the database administrator, the schema designer, and the end user. With KDB Plus, all 3 teams can be combined into one. An analyst obtains data, records it into a KDB Plus database, and later analyzes the data themselves. This is all possible because KDB Plus, though in name is a database, is merely a combination of the file system and the Q programming language. Backups, permissions, and segments are all delegated to the file system. Creating, deleting, and modifying tables are all features of the Q programming language or the file system. So, you have probably learned other programming languages. Many people nowadays use Python. People use C++ in finance as well, and a few other programming languages, Rust, for example. Right, so you would have seen other programming languages. But what makes Q different? What distinguishes Q from other programming languages? Why, after all, are there considerably fewer Q programmers than there are, for instance, Python programmers? Well, let's think about it. Most of the languages that you have encountered in your career would be derivatives of C. They are said to belong to the C family of languages. Even Python does, even though it probably stands out from that family of languages. But many of the programming languages that we use nowadays are members of the so-called C family of languages. C itself was designed by Dennis Ritchie and developed by Dennis Ritchie and the Bell Labs, first appeared in 1972, was significantly influenced by B. In fact, the name C implies that it's an upgrade on B. B is also known as BCPL. And it was influenced by a few other programming languages that you may have heard of: Algol 68, Assembly, PL1, and Fortran. Okay, now C is a relatively simple language. It's very close to the metal. It allows you to do stuff which is very close to the metal. It gives you control over the machine. So it supports the so-called imperative, procedural, and structured paradigms, the basic paradigms of programming. We'll see what they actually are. We'll see what distinguishes them. And so this is a typical piece of C code, right? It includes stdio.h for input-output. Everything in C belongs to one function or another, right? So in this instance, right, there is this function main that is going to add up the numbers, the first n numbers, and it will display the sum of those numbers, right? So we see the characteristic curly brackets, something that we see a lot in the C family of languages, apart from Python. And then there was an upgrade on C, the C++ programming language, which was designed by Björn Strustrup. So as a matter of fact, Strustrup took C and he took another programming language called Simula, which now introduced these higher level programming concepts called classes, which mapped onto real world constructs. For example, a person may be represented as a class, or a matrix, or indeed a car, or something like that. And then you could have instances of these classes called objects, right? So that allowed you to combine this low-level approach of C with this ability to model real-world concepts quite effectively. And that is something that C++ introduced, Björn Strustrup C++. Now, this is a language that is managed by a C++ standards committee. It first appeared in 1985, and it added to the paradigms of C the functional, object-oriented, and generic paradigms. In fact, C++ is a multi-paradigm language. But if you look at it carefully, the code quite closely resembles the code that we have already seen in C. It has classes, and indeed here we have a class. And well, in this simple example, we could have gotten away with just the C struct, but okay, we do have a class here, and so now we can combine and encapsulate data and functionality into classes, and create objects of those classes. But if you look at the style of the code, it looks very similar to what we have seen in C. Then C also introduced templates, and with it the ability to do this template metaprogramming, something that can be, you can compute a lot of stuff at compile time as opposed to at runtime. So that's another typical feature of C++. This ability to somehow manage the when stuff gets computed at compile time or at runtime. And then Java came along, developed by James Gosling at Sun Microsystems. It appeared in 1995. Originally, this was an attempt to simplify C++, to get something that would have the advantages of C++, but would run on something like a vacuum cleaner. But the language ended up being enormous, overtaking C++ in size and in the complexity of its standard library, of the Java JDK, Java Development Kit. The language was originally called Oak, and it became the kind of language that you need where you probably cannot compete directly with C++ in terms of performance, but you have this reliability. You don't necessarily need low-level memory access. You have garbage collection, but it's something that can run portably in many different architectures. Okay, and it has this very strong, kind of very prescriptive type system. Something that allows you to, the IDEs, to do a lot of work, a lot of refactoring work, perhaps more than you would normally get in C++. Then you had C#. C# was to a large extent inspired by Java, but it was also inspired by functional programming, and it was introduced by Anders Heilsberg into the Microsoft family of languages, into the Visual family of languages. And this programming language supports structured, imperative, object-oriented, event-driven, task-driven, functional, generic, reflective, and concurrent programming. As it were, this is a pun, or the name of the language is a pun on C++, because we have the C#, which is plus, 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 in 2 dimensions. The languages that we have considered so far belong to this C++ family of languages, but there were other languages, quite different. They belong to different programming paradigms, such as Lisp, which you would know if you use the Emacs code editor on Linux, for instance. Now, Lisp was designed by John McCarthy to capture how people think, to capture the idea of logic. It was then developed by Steve Russell, Timothy Hart, Mike Levin, first appeared in 1958, was influenced by IPL, and it supported kind of functional, procedural, reflective, and meta paradigms, but it's primarily a list processor. In order to program in Lisp, you need to think in terms of lists and operations on lists. You see, so this is this my_append function. And if you look at the code, it looks quite different to the code that we have seen so far from the C++ family of languages, from the C family of languages. That's yet another programming paradigm is functional programming, pure functional programming, and a classic example in functional programming, which is studied in many computer science departments, is Haskell, named after the logician Haskell Curry. So again, if you look at Haskell code, which is functional code, now everything is a function in the mathematical sense, and these functions are defined in terms of recursion, in terms of base cases and recursive cases, as you can see in this example, in these 2 examples, actually implementing the towers of Hanoi and Fibonacci numbers. So you see there is the C family of languages, which shares many of the same ideas. There is Lisp, which is kind of on its own. And there is Haskell, which is a pure functional programming language. So we see that that not every programming language belongs to the C family of languages. Perl, for example, Perl, I don't know how many of you have programmed in Perl, which appeared in 1990, designed and developed by Larry Wall. Now, Perl is, again, quite unique practical extraction reporting language. In Perl, there is a lot of functionality for dealing with strings, even though it shares many of the features that we see in the C family of languages. It shares, for example, the same structures, such as while loops. It shares the curly brackets, but it does come with, for example, regular expressions that allow you to do fairly sophisticated operations on strings, such as here we see a regular expression, one of the core features of Perl, which migrated into Python as well, but now as a module as opposed to as a language feature, because in Perl, these regular expressions, a very powerful set of tools for dealing with text, they existed as a language feature. They existed at the level of syntax, and it's not the same in Python. Well, of course, Python, I would say that Python, to a large extent, it almost belongs to the C family of languages. It comes with many other ideas, which came, for example, from functional programming. It incorporates many reflective elements, the kind of elements that we have seen in Java, for example. And when he began implementing Python, Guido van Rossum, the author of Python, was also reading the published scripts from Monty Python's Flying Circus, a BBC comedy series from the 1970s. Van Rossum thought he needed a name that was short, unique, and slightly mysterious, so he decided to call the language Python. And nowadays it's effectively the lingua franca of much of data science, machine learning and AI. And again, so it took many ideas from other programming languages. It borrowed these ideas, so we can see, for example, that there are regular expressions, but they were done in a Pythonic way to avoid making the language too large, to avoid using syntax. It's using standard Python techniques such as modules and function calls and so on. Thus, we have seen many different languages already, belonging to many different programming paradigms. Let us very quickly review these programming paradigms. So there are declarative languages. They express the logic of computation without describing its control flow. They consist of declarations. So, for example, SQL is declarative. Many of them are event-driven, so the flow of the program is determined by events, quite often external events, such as user actions, sensor outputs, or messages from other programs or threads. Functional programming treats computation as the evaluation of mathematical functions, and it avoids changing state and mutable data. It prefers pure functions that have no side effects. Generic algorithms are written in terms of types to be specified later. So we don't want to restrict the types too early because we want the same code to work in different types, and that facilitates code reuse. Imperative, this is probably what most people think when they think of programming languages. They use statements that change a program's state in much the same way that the imperative mood in natural languages expresses commands. An imperative program consists of commands for the computer to perform a sequence of steps. Imperative programming focuses on describing how a program operates. Do this, do this, do this. Meta. Computer programs treat other programs as their data, including their own code, so a program can be designed to read, generate, analyze, or transform other programs, and even modify itself while running. Object-oriented, based on the concept of objects, which originates in Simula, which can contain data in the form of fields or properties or attributes, and code in the same of procedures, also known as methods. Procedural, it's a programming paradigm. It was quite common in C, derived from structured programming based on the concept of procedure call, although procedures quite often are called functions. But they may also be called subroutines or routines. And the idea is quite simple. Break the program down into functions or procedures so that you can reason about it in terms of those procedures. And it also organizes your code. Reflective, very similar to meta. Programs have the ability to examine, introspect, and modify their own structure and behavior. Right, so meta tends to be applied to other code, whereas reflective programs, they tend to work on their own code, and they tend to reflect their own code. Structured, well, it's having if-then-else, loops, for loops, while loops, block structures and subroutines. Many languages that you have encountered are structured programming languages. But what I'm going to tell you now is there is another family of languages which you probably haven't heard of. Maybe you have, but then you are probably quite a rare individual if you have been exposed to APL. This is a programming language that was designed by Kenneth Iverson and developed by Larry Breed, Dick Lathwell, Roger Moore, and a few others. It first appeared in 1966, and to a large extent, APL was influenced by mathematical notation. And some of the ideas that it implements, first and foremost, it's an array programming language. Arrays, collections of data, are first-class citizens in APL. Everything generalizes to these vectors or arrays. There are elements of functional programming, there are elements of structured and modular programming in APL. APL is an acronym for A Programming Language, which is also the name of an eponymous book which was published in 1962. There are several ideas behind APL. One is stored program idea, which dates back to John von Neumann. It amounts to the idea that program itself is data. Program code is data and should also be stored in the same memory space. That's the stored program idea. And the second idea is the idea of efficient notation. The idea that developing a concise, expressive syntax is critical to solving complex iterative problems correctly and efficiently, and that idea was pioneered by Iverson. He used the inspiration from mathematical notation, because he thought that mathematical notation quite successfully achieved its goals. And so in the preface of a programming language, Iverson defines a programming language in the following terms. Applied mathematics is largely concerned with the design and analysis of explicit procedures for calculating the exact or approximate values of various functions. Such explicit procedures are called algorithms or programs, because an effective notation for the description of programs exhibits considerable syntactic structure. It is called a programming language. And he reviewed the efficient notation idea, which he introduced in APL, in his Turing Award lecture entitled Notation as a Tool of Thought. The advantages of executability and universality found in programming languages can be effectively combined in a single coherent language with the advantages offered by mathematical notation. And Iverson's notation was effective as it was simple. It relied on simple rules of precedence based on right-to-left evaluation. There would be no more precedence tables. It built on ideas from linear algebra, tensor analysis, and operators a la Oliver Heaviside. The fundamental data structure in APL is a multidimensional array, sometimes referred to as a multidimensional vector. Languages such as APL and its progenitors are sometimes referred to as array programming languages, vector programming languages, or multidimensional programming languages because they implicitly generalize scalar operations to higher dimensional objects. The notation was further elaborated at IBM Research, where Iverson worked alongside Adin Falkov from 1960 until 1980. The two of them collaborated very closely, and the collaboration between Iverson and Falkov would span nearly 2 decades. Iverson's notation was known as Iverson's notation within IBM until the name APL was suggested by Falkov. After the publication of A Programming Language in 1962, the notation was used to describe the IBM System 360 computer. Iverson and Falkov then focused on the implementation of the programming language. An implementation on System 360 was made available at IBM in 1966, and then it was released to outside users, to the outside world, in 1968. And on this slide, we see an example of what APL looks like, APL code looks like. We see comments on the right that explain what that code does. Drop 2, mat with 1 entry per row. Length of address, align the names, address names, change underscore to blank. Names, length of last word in name. Okay, so let us perhaps look at how this code is typed. It's typed using specialized keyboard, where there is a set of symbols. You see there is a set of these triangles and arrows and so on that corresponded to the operations that were considered important enough to include them as primitives in this language. But there is a minimal set of primitives. They were quite well thought out. What did you actually need to successfully manipulate these objects, these arrays? This is another view of the APL2 keyboard layout. If you want to, you can find a simulator for APL keyboard, and you can also find the corresponding fonts. But you will be pleased to know that even though K, Q, and KDB by extension are derived from APL, they do not use the APL keyboard. They use the standard ASCII character set. All this work on APL was conducted at this IBM research facility, headquartered at the Eero Saringen Design Thomas J. Watson Research Center in Yorktown Heights in New York. And here we see several developers of APL. From left to right, we see Dick Lathwell, then we see Ken Iverson, Roger Moore, Adam Falker, Phil Abrams, and Larry Breed. And on the extreme left in the background, we see John McGrew. This photo was taken in the IP Sharp Associates Hospitality Suite during the 1978 APL users meeting in Toronto, Canada. So in 1980, Iverson moved from IBM to IP Sharp Associates, IPSA. That was a Canadian APL time-sharing consulting and services firm. He was preceded there by several of his IBM colleagues, Paul Berry, Joey Tuttle, Dick Lathwell, and Eugene MacDonald. IP Sharp Associates, sometimes pronounced APSA, they focused on the APL language and systems around the APL language. The APL language group was managed by Eric Iverson, who was Ken Iverson's son. Roger Moore, one of the APL 360 implementers, was a vice president. It is at IPSA that Kenneth Iverson met Roger Hui and Arthur Whitney. Arthur Whitney was an intern at IPSA, and the three of them continued to work on APL, adding new ideas to the programming language. Roger's family emigrated to Canada from Hong Kong in 1966, and he was first exposed to APL before he joined IPSA at the University of Alberta. Whitney had a background in pure mathematics and had worked with APL at the University of Toronto and Stanford. He met Iverson for the first time well before he joined IPSA because his father was a college friend of Kenneth Iverson at Harvard. So he spent some time as a child at Mount Kisco, where Whitney's family lived at the time. Whitney's family lived in Alberta, but Iverson lived at Mount Kisco, where Whitney would visit, and he would learn APL programming from Iverson. So here we see some APL-related memorabilia, such as the APL users meeting from 1982. We also see the proceedings of the Information Center and changing technologies. And IPSA was a very interesting company. It was very creative. A lot of people who worked at IPSA ended up opening their own companies or making serious contributions to computer science or computer business, as it were. So we see Bob Bernetsky, founder of Snake Island Research, Clark Bruce, founder of Soliton Incorporated, Git Christensen, who founded Insight Systems, and he was CEO of Dialog Limited. Lib Gibson, who launched Simpatico ISP, was CEO of Raft Mobile Systems, CEO of Bell Globe Media Interactive. Leslie Goldsmith founded Affinity Systems. Rob Hodgkinson founded Financial Market Software Consultants. Roger Hui developed the programming language J, which is another APL variant with Ken Iverson. Hugh Heinemann founded Affinity Systems. Eric Iverson founded J Software Inc. Rohan Jayasekara founded the Simpatico Internet Service. Morten Kromberg founded Insight Systems and served as CTO of Dialog Limited. W.H. Lindington founded Beyond 2020. Jane Minette founded the Simpatico Internet Service. Ronald Plesch was principal of Cygnus Solutions. Richard Proctor founded APL Borealis Inc. Scott Remberg founded the Simpatico Internet Service. Morgan Smith founded Bregan Inc. Stephen Taylor was a writer, editor, poet, and founder of the Iverson College Conferences. And Arthur Whitney founded KX Systems, developed A+, K, and Q. So now let us focus on the work of Arthur Whitney. Arthur Whitney went to work for Morgan Stanley in 1988. And some of us who have worked at Morgan Stanley, a while ago I have worked at Morgan Stanley, will remember that Morgan Stanley still used to have, in the early 2000s and mid 2000s, they used to have a programming language called A+, which used to run on IBM mainframes. And that was an APL-like programming language which was developed by Arthur Whitney for Morgan Stanley when Arthur Whitney was there from 1988, specifically to work with financial time series and process large volumes of time series data. Now, unlike APL, A+ allowed functions to have up to 9 formal parameters, use semicolons to separate statements, much like C or C++, use the last statement of a function as its result, and introduce the so-called dependencies which functioned as global variables. You can download APL Plus from, sorry, not APL Plus, A Plus, from www.aplusdev.org. And you can use the KAPL font, which includes the special characters used by APL and A Plus to program in A Plus. Well, that's the Morgan Stanley's office in New York, in Manhattan. So what happened a little bit later, because Arthur Whitney joined Morgan Stanley in 1988, one summer weekend in 1989, Whitney visited Iverson at Kiln Farm and produced, on one page and in one afternoon, an interpreter fragment on the AT&T 3B1 computer. Roger Huey studied that fragment and on his basis developed an interpreter for another APL variant, J. Unlike APL and A+, J used the ASCII character set, and it included advanced features such as support for parallel MIMD operations. Whitney's original fragment appears under the name Incunabulum in an appendix in Huey's book, and you can easily read this online, so you can look at the code that was written by Whitney. So other ideas by Whitney found their way into J, orienting primitives on the leading axis, using prefix rather than suffix for agreement, total array ordering, and so on. Ken Iverson, his son Eric Iverson, and Huey all ended up working in a company called J Software in the 1990s and 2000s. But Whitney, at the same time, Whitney left Morgan Stanley in 1993, so having developed A+ for Morgan Stanley, he co-founded KX Systems with Janet Luzgarden, and then he developed another APL variant that was called K. On its basis, he developed a columnar in-memory time series database called KDB. Okay, so you see Q was added later. We'll see when Q was added. So KX Systems was under an exclusive agreement with UBS, but that agreement expired in 1996, and K and KDB became generally available. So KSQL was added to the language in 1998 as a layer on top of K, and some developers regard it as part of the K language, but it's actually kind of a macro layer on top of K. It included SQL-like constructs such as select. That's the UBS office in New York in USA. And let us look at what K looks like. We see that it looks nothing like the languages that you may be used to, such as C++ or Python. So this here is an example of K code. You see what it does. You see, if we just do hash colon on X, right, it will return the length of X. But if we do hash colon apostrophe X, it will do the length on each element of X, right? And the elements of X, as we can see here, are strings. So we apply length to each element of X. Then we have this greater than. What it will do, it will sort the indices. It will sort the indices of the given array. And remember, it's all computed from right to left. So it will be, so it will sort the array of these lengths, right? It will sort them in descending order, right? And then what we'll do X at we will apply at, we will take the elements of X at those indices, again, proceeding from right to left. And by doing that, we basically sort the list of strings by their length in reverse order. So we have 3, 7, 8, the strings of length 5. Then we have 4 and 5, the strings of length 4. And then we have the 3 strings of length 3, 1, 2, and 6. So you can run this code from your Q interpreter, but Q expects Q code by default, so you have to either prefix it with K parentheses like this, or you would have to use a backslash to switch into the K mode from Q mode, and then another backslash on a new line will take you back to the Q mode. Okay, so now we understand what this code does. This is probably your first piece of K. So what happened is KDB was pretty much rewritten in its entirety and released in June 2003 as KDB Plus. It was a more or less complete rewrite of KDB in 2003. And it was also rewritten to target the 64-bit systems, which by now became common, and it consisted the fourth version of the K programming language developed by Arthur Whitney. And on top of the K programming language, to make it a little bit more user-friendly, to make it a bit more human-readable, a macro language level, Q, which stands for query, it was a query language, hence the name, was developed in terms of K and defined in terms of K. Now, Q was also an APL-inspired language, but it was designed to make the language a little bit more accessible, right? So you didn't have to memorize all the symbols and what they meant. So both Q and K compile to the same bytecode that is executed by the KDB byte interpreter. For example, type in Q is equivalent to @: in K. Q is much more readable than K, and most KDB Plus developers write their code in Q and not in K. And then also in KDB Plus around the same time, 2003, another layer was added on top of Q, which was called Q-SQL, which in some ways resembled the traditional SQL, but it's not kind of a faithful implementation of SQL. It has its own kind of quirks as opposed to SQL, and we'll look at them when we get there. So Arthur Whitney was interviewed in 2004, and he described this update to the programming language as another jump in performance and productivity. With KDB Plus, we have merged the K and K-SQL languages into a single language for queries, time series analysis, and general programming. This means that customer programs will be smaller and faster to write. And by now you will see that Arthur Whitney has this belief in having terse code, small code, not a lot of code, being efficient, because according to Arthur Whitney, only short programs have any chance of being correct. Now, by then, KDB had quite a following, which has continued to grow since the 2000s. And nowadays, some of the KDB users, I'm going to list them, are Australian New Zealand Banking Group Limited ANZ, B2C2, which is a cryptocurrency market maker, BAML, Bank of America Merrill Lynch, Barclays PLC, BGC Partners, a broker, Capgemini SE, Citadel LLC, CIMB Bank, Citigroup, Commerzbank, CC&L, Connor Clark and Lund Financial Group, CPP Investments, Crédit Agricole, Credit Suisse, Deutsche Bank, Formula One team, interestingly, the Goldman Sachs Group Inc., HDR Global Trading Limited, which operates BitMEX, and in fact BitMEX was founded by, it's a cryptocurrency exchange, was founded by KDB enthusiasts, including Bandello, HSBC Holdings PLC, JP Morgan Chase and Company, LiquidNet, Macquarie Group, Marshall Wace, Millennium Management, Morgan Stanley, NatWest Markets, Nomura Holdings, Point72, also known as Cubis Systematic Strategies, Quantal Technologies, Royal Bank of Scotland, RBS, RX Data Science, Singapore Exchange, SGX, Square Point Capital, Standard Chartered, Stanchart, SIG International Group, Simigan, which is a joint venture between KX and Nagler and Company, Thomson Reuters, Refinitiv, Tibra Capital, UBS Group, Vanguard, Westridge Markets, and Winton Capital. Thus, Q is a programming language designed in the tradition of APL, so embracing Ken Iverson's efficient notation idea with very terse syntax, again because according to its creator Arthur Whitney, only short programs have any hope of being correct. Q is interpreted. It requires no compilation phase. All functions are compiled into bytecode at runtime. Dynamic in both function definition and variable types. Event-driven KDB processes can be written as event handlers. Thus, this demultiplexing of the concurrent messages and the synchronous invocation of callbacks allows KDB to be used as a complex event processor or a CEP system. It's functional. Functions are first-class citizens, but it is not pure functional because the functions may have side effects in Q. And it's like all APL variants, it's vector-based, it's an array language, it generalizes operations on scalars to work on lists as well. So if we look at all the various programming languages that we have mentioned, Python, C++, Java, C#, KDB plus Q, they all have their distinct ecological niches. So Python is the language of data scientists, it's the language of hackers, it's the language of scripting as well in Linux. But a lot of the ML work and AI work is typically done in Python unless you need C++ for speed for real-time systems. Java, C# are usually used for building microservices. C++ and perhaps to a lesser extent Rust are used by HFTs. Java and C# are rarely used by HFTs. KDB plus Q has its own unique niche. Wherever you have big data or dynamically arriving data and where latency and throughput are of the essence. KDB plus Q is often utilized in algorithmic trading, for example, but also in other real-time data applications such as Formula One racing. But you don't necessarily have to use it exclusively. Quite often it's used as part of an ecosystem with other programming languages, typically C++, C#, and Java. For example, some of the languages will be used to build GUIs and so on. KDB is used specifically, for example, for data capture, access to real-time data, some analytics, things like that, for storing historical data, for access to historical data, for querying the data. So, you can, when you're engineering a system, it doesn't have to be, some systems are pure KDB systems. Sometimes people mix these different languages together, and I've built, for many different institutions, I've built systems of both kinds, kind of pure KDB systems, but also kind of various hybrid systems. So let's look a little bit more closely at the Q programming language. So here we do the vector addition, right? And the two vectors, 20, 32, and 24, and 17, 3, and 12, are added element-wise. So the result is another vector or list in the Q parlance. It's 37, 35, 36. Here we have lists of lists. We have two lists of lists, which can be used to represent matrices in KDB. Now these are lists of longs. When we talk about matrices, we tend to think about lists of floats in KDB. But the result of this addition is the list of lists of longs again. And notice that when we enter something like 2 times 1 plus 3, it will be evaluated from right to left. So the addition will be evaluated before multiplication. This is not what we usually do, because 2 times 1 plus 3, according to Q, because it does 3 plus 1 first, that's 4, and then multiplied by 2, it's 8. Now, if we were to do it using the usual kind of conventions, which include the operator precedence, so times has precedence over plus, so that would be 2 times 1, that would be 2, plus 3, that would be 5. Okay, so in order for us to get this 5 in Q, we would either have to reorder the expression or put some parentheses in. So, for example, if we put the parentheses around 2 times 1, then that will be evaluated first. Okay, so then we will have 2 times 1, that's going to be 2, and then plus 3, again, we then go right to left. If we go right to left, it's actually add 3 to this term, which happens to be 2 times 1, that's 2, and we end up with 5 in that case. So you can see we can use parentheses to obtain this result that we were expecting based on the precedence tables, which Q doesn't use. This slide demonstrates that functions, and they're these objects that are introduced using curly brackets, are first-class citizens in Q in the Christopher Strachey sense. So the type of 2 times 1 plus x is a lambda, 100h. We can assign that lambda to a variable such as f colon, that's the assignment operator. So we can assign a function to a variable. That's how functions obtain their names, through assignment to variables, unlike many other programming languages where there is some sort of syntactic sugar for introducing named functions. Then we can pass functions as arguments to other functions. So here you can see that the function f is passed as an argument to another function called g. Here we see that we can project the function by partially fixing the arguments of that function. So for instance, g used to be a function of 2 arguments, but we fixed one of the arguments, and therefore we ended up with a function of so g was a binary function, but then we fixed one of the arguments and assigned that projection to h, and we ended up with a unary function h. And the type of h is a projection. I mean, we don't necessarily have to distinguish projections from ordinary functions, but Q does under the hood. We also have another interesting construction, which is a function composition. So here we have composed functions log and h over here using the function composition syntax. And the type of h1 is going to be a function composition. But although we have all this machinery for functions, we do not really call Q a pure functional language, because, as in this example, the while loop, even if we put it inside a function, can modify the globals a and b, which implies that the function has side effects. Okay, so this is not something that is typical of pure functional programming languages. And of course you will see that this code computes the Fibonacci sequence. Now, it used to be the case where the Q syntax was subdivided into nouns, such as, for example, numbers, which are atoms, so and symbols, and lists are also nouns, dictionaries are nouns, tables are nouns, and then there is stuff that acts on these things, verbs. So, for example, 10 mod 3, which we write in infix notation as 10 mod 3, but we could also write it in prefix notation, mod square brackets 10 semicolon 3 close square brackets. So this is a dyadic function mod, which we can write in both ways, infix or prefix notation. That's a verb. A function application is a verb, and primitive operators act as verbs. But unlike many other programming languages, we have these higher level functions, adverbs, that take other verbs and modify them. and that's the term adverb. So, for example, we have the verb plus, which, if we did 0 plus 9, 8, 12, we would get 9, 8, 12 as a result. But if we modify this plus using an adverb slash, which is actually called fold, also known as over or reduce over, then we obtain a different result, 29, when we're using this verb modified by this adverb. Thus, we can think of the word order in Q as noun, verb, adverb, noun. So again, this differs from many other programming languages. There are quite a few different adverbs in Q, and it may be a good idea for you right now. We will come back to adverbs, but it may be a good idea for you to look at this slide and kind of ponder over this slide. So we have both. We have fold, we have scan, we have each right, each left, each prior, and we have the Cartesian product, which is the each left, each right composition. It may be a good idea to just pause this slide and play with these adverbs in the Q interpreter. Another interesting feature of Q is that it has temporal types, and they're supported natively in the language. So we have dates, we have times with millisecond precision. We have date times, which are it's what it says in the tin. They consist of date and time in millisecond precision. There's also timestamp, which has nanosecond precision, which may be useful if you're building high-frequency systems, high-frequency trading systems or robotics. You also have time spans where the duration is in nanoseconds, month, minute, and second. You can have corresponding lists of dates. For example, that's 14H is a list of dates. And Q supports arithmetics with dates and other temporal types, with timestamps and so on, and casting. So we can take one temporal type and cast it to another temporal type, as in this example here. But then, of course, what makes it it's a database is the fact that tables are also first-class citizens, and it's type 98H. That's a table, and that's the syntax that we can use to create a table. They can also be thought of as flips or transpositions of dictionaries, and this kind of native support for tables in memory tables, but also tables mapped to disk, is what ultimately makes KDB a database. So tables can be keyed, which is useful for indexing. We can remember this kind of index mapping for this table. They can be sorted, and when we sort a table, this is reflected in the attributes of the table, which are accessible using meta. So SQL, which is the primary database language, which was designed by Donald Chamberlain and Raymond Boyce, and first appeared in 1974, became the language for databases. What we have in KDB instead of SQL, we have a QSQL, which is a programming language layer on top of Q, which provides a superset of SQL functionality, although there are significant differences in syntax and semantics between SQL and QSQL. Whereas SQL is based primarily for security, for reversibility, for example, of transactions. QSQL is designed for speed, and so KDB doesn't attempt to be an ACID database, unlike many traditional database management systems. KDB Plus, compared to especially traditional database systems, offers decreased memory footprint, much faster execution, quicker prototyping, thus opening up new business opportunities, particularly in the context where you have time series and big data. Q natively supports MapReduce operations. So again, if we read this from right to left, we generate 10 million random numbers in the range of 0 to 10F. Then we batch them in batches of, we generate 100 million of them. Then we batch them in batches of 10 million. So we end up with 10 batches. And then to each of them, we apply this function, we compute the average log. And then we end up with these 10 average logs. And then we we have mapped this function, and then we do the reduction. We add up all of these average logs, and we end up with this 13.02 something. Right. Now we can time these. And notice that in order to parallelize this MapReduce construction, all we need to do is add a single letter P in front of each, and we will start using the slave threads that we have locally. So this is peach is a parallel each, but in order to make sure that, in order to be able to utilize this parallelism, make sure that you have actually launched KDB with slave threads enabled. So if you think about CPU organization, you will remember that there are multiple cores, each with its own register bank. That's the fastest memory you can possibly have. And then there are caches. Level 1, level 2 caches are typically specific to each core, whereas level 3, level 4 caches are shared among the cores. Then this whole system interacts with main memory. Now, in order for your program to run fast, you need to make sure that you get the minimum number of cache misses and that you fit into the level 1 cache ideally, if not then into level 2. So this graph was obtained by varying the size of the accessed area in bytes, and we then see that when we no longer fit into the level 1 cache, there is an order of magnitude decrease in performance expressed as CPU cycles per value. So KDB was optimized to use level 1 and level 2 caches. There are other optimizations. First of all, thinking of the stored program idea, the code lives right next to the data, so there is no need to spend time transmitting one to the other. KDB Plus is a columnar-oriented database management system. That is one that stores data tables as columns rather than rows, unlike many traditional DBMSs. And that makes optimal use of locality. So think about queries that do, that do full table scans. They're common in analytical workloads, but they only need to access the columns that they touch. Whereas in row major formats, you would require a full scan of the entire table. The column-wise format allows you to read only the relevant columns, and that's a more typical use case in time series processing. Real-time data is typically stored in memory. Historical data is typically stored on disk, also column-wise, and both HDDs and SSDs are at their most efficient when reading data sequentially from disk, and data is typically read in 4096 byte blocks. The Q programming language naturally lends itself towards the construction of terse and efficient code. It is vector-based, and its vector operations are really quite fast. Loops can be avoided in many cases if you think carefully about your code structure. Q data structures are very compact. The language is heavily optimized and makes extensive use of L1 and L2 caches. Column attributes, which are another feature of KDB Plus, supported natively at the level of the language, they allow you to optimize the execution of QSQL queries. Q supports parallelization either via Peach or via .q.fc. There are many clever optimizations behind the scenes for important special cases as well, and a lot of code is written in optimized C. Also, KDB Plus is consistent with recent trends in computing, where there is a reduction of the cost per megabyte of main memory, the increase in the number of cores per CPU on commodity processors, memory is getting larger, vector operations such as SIMD, SSE, AVX512, they're getting faster, and they're utilized by KDB. KDB also, as of KDB Plus 3.7t, supports Intel Optane DC persistent memory, which is a relatively recent technology. Intel Optane DC persistent memory, supported on second generation Intel Xeon scalable processors, is a game-changing technology from Intel, which allows KDB Plus users to increase the performance and capacity of their applications. Users are able to specify, explicitly designate which data fields to store in DRAM and which ones to store in the much faster persistent memory, thus effectively tiering the hottest data into the lowest latency resource for higher overall performance. There are a number of books that you can read in conjunction with this course to learn and to optimize your learning of KDB and Q. One of them is Q for Mortals, a classic by Geoffrey Borrow. It is a series of tutorials based on Q snippets intended to be entered interactively into the Q console by the reader. There is also Q-Tips, a practical guide to learning the language through building a real-life application. It's filled with many useful examples and in-depth explanations. There is also Machine Learning and Big Data with KDB plus Q, which I have co-authored with Jan Novotny, Aris Galiotis, and Frédéric Deleuze. The book covers data description, summary statistics, basic regression methods and co-integration, vol estimation and time series modeling, machine learning and other systems, game engines, agent-based models, and it basically starts with an introduction to KDB and shows you how to implement all that in KDB. There is also FunQ, which explains how to implement many of the most famous machine learning algorithms in Q. This book is also written by Nick Saris. There is a plethora of resources on the web that you can use to advance your knowledge of Q. There are tutorials, knowledge base, there is a phrase book, a list of some common examples in KDB, a very useful reference card, a collection of code on GitHub, interfaces to other programming languages, Excel integration. The book Q for Mortals is online. Our library, QuantQ, which we implemented in our book, is also online. Nick Saris's GitHub repository, time-stored KDB Plus tutorials, Aqua Analytics KDB Plus resources, and a number of blogs that you can access if you want to learn KDB. This is the bibliography that and the resources that I mentioned throughout this lecture, and I would like to thank you all for listening, and I hope that you enjoy learning KDB. See you in the following lectures. Have fun.